Well, good morning, everybody, or good afternoon for most of you, maybe. I'm speaking to you from Santiago, de Chile. And as Danny said, I'm the instrument scientist on VISIR. And I want to thank the scientific organizing committee for asking me to give this talk on VISIR. They specifically asked me to talk about the operations, the calibrations, and the upgrades that VISIR has undergone in the last, since its inception in 2004. So on the operations side, I will try to give you maybe a little bit more of information on what VISIR does and how ESO manages the instrument. So a little bit the tip of the carpet or tip of the curtain in the inner workings of managing and operating an instrument. Of course, I will also give you or basics on the instrument. I mean, it's an infomercial on VISIR for those people who are not using this particular instrument. Of course, I encourage you to do so and look at it. And so I'll try to get you, say, up to speed with what VISIR is and what VISIR does and what VISIR can deliver in terms of science. We'll speak a bit about the calibrations, how ESO manages the calibrations, how we do things at night, how we do things in daytime, how we do the quality control. And in the end, I will try to give a brief overview of the technical parts of the upgrades. So the upgrade with capitals that took place between 2012 and 2015, basically. And the upgrade that was basically the near upgrade, which has been presented a couple of times already, so I won't spend much time there. But at least I would like to give you some insight in what we still can do with VISIR. Now VISIR will move to UT2. So to get everybody up to speed of what VISIR is. So VISIR is the VLTI, the VLT imager and spectrometer for the mid-infrared. So it was built by a Franco-Dutch consortium led by the COA. It is located, well, it is supposed to be located currently at the Cassegrain focus of UT2, were it not for the current situation. Of course, VISIR has always been on UT3 since 2004, which is well, good to realize, because VISIR as an instrument has a high demand on the actual telescope performance. And so there were, especially after the upgrade, and during the upgrade, there were a lot of interactions going on between the image quality, optimization of VISIR, and the actual behavior of the telescope. But as said, it will go to UT2 now, and this will not happen before December 2020. It will be at the earliest, probably in January 2021. Of course, this is as a result of the near experiment, which took place on UT4 with the deformable secondary mirror. The reason why to put VISIR now on UT2 and not on UT3 has to do with the pressure on the telescope. There's a high pressure. There was a high pressure on UT2 with flames UV and X shooter, and the pressure on UT3 was a little bit less. So the exchange has been to put the UT2 Cassegrain instrument X shooter on UT3 and vice versa to put VISIR on UT2. So VISIR was conceived as a multi-mode instrument, and so actually VISIR has two arms, basically an imaging and a spectrographic arm, with each their own optics and each their own detector. So what does VISIR provide? Well, imaging and spectroscopy, obviously, imaging in the M band, N band, and Q band, and spectroscopy in low resolution for a full M band, and in high resolution, long slit and high resolution cross dispersed. Then in the imaging arm, you also have the opportunity to do sparse aperture masking and chronography. In the imaging arm, the field of view and the small field objective is 38 arcsecond squared with a pixel size of 45 microarcseconds. In the small field, there is also an intermediate field objective, which is basically never used because with the larger angle on sky, the background just increases. Well, double in this case, which means that the detector integration time has to be reduced, which means that you have to window, which means the whole point of it having a larger field becomes obsolete. And the detectors on both spectroscopic arm and imaging arm is an Aquarius. So in operations, so first I will go a little bit through what VISIR does on the inside to get you an idea, a basic idea of how the light path is and what it allows to do. So this is the imaging arm. So the light comes in through an entrance window, and after the entrance window, everything is cryogenically cooled. There's a diaphragm wheel that will adapt the aperture field for the magnification by the TMA optics. The diaphragm wheel also allows to move the light either in the imaging arm or in the spectroscopy arm. Then the M1 mirror basically images the pupil where the filter is located in the cold stop. The M2 is just a folding mirror. And then you have the three objectives in the TMA optics that put the light onto the detector. The detector is an Aquarius, and as said, it's at a 38 arcsecond field. And has a 45 milliarcsecond angle on the sky per pixel, which basically oversamples the PSF a lot, but given that your background limited, this doesn't really matter. So the imaging arm has 5 reflections, basically, 5 mirrors. It has 3 wheels, the diaphragm, the filter wheel, and the TMA optics is another wheel, and a single detector. Then in the spectroscopy arm, so on the top you have the same diaphragm wheel. Now the light is deflected into the spectroscopy arm, goes through the filter wheel for the acquisition, then it goes to the slit wheel, and then some reflections either to the left. So basically there are also 2 arms in the spectroscopy arm, 2 sub-arms basically. To the left, where you have the prism for low resolution and you have a medium resolution grating, or to the right where you have a high resolution, a shell, before it lands on the detector. So a bit more reflections in the spectroscopy arm. Then the detector itself, so in the first stages of the VISIR operations, this was a 256 detector, which was replaced in 2012 for the principal reason of the small field of view and because of the bad cosmetics. So this was improved with the Aquarius detector, with a larger field of view, better cosmetics, but it was discovered that it suffered from what is called excess low frequency noise, which is basically correlated noise in each read, which doesn't allow you to go to signal to noise ratios that you in principle expect because of this correlated noise. So faster chopping mitigates this, which is then implemented as well in VISIR. So in the old VISIR, so the VISIR that operated before 2012, the chopping was less than a hertz, and the new VISIR chopping is generally about 4 hertz. So the detector shows a little bit of a pedestal, as you can see on the right corner. This effect we tried to mitigate in 2017 by having a different readouts, which was mitigated effectively to a certain extent. And importantly, both the old detector and the new detector, they provide burst mode. This image was showed a couple of times this week, and I liked it a lot, by Cavella in 2007 on a BE star, I think it was. As the burst mode allows you to get instantaneous PSF and do a poor man's AO, basically. Of course, burst mode has some limitations. You need to have enough noise in each single readout, each single DIT, and so it limits the type of objects that you can do in this talk. I was also impressed by the overview on the massive star evolution and the amount of work and science results that have been achieved by using burst mode. And so it's essential for mid-infrared. And I'll come back to this a bit later. So then the telescope, of course, it does classical chop nodding to get rid of the background. So nodding with the M2 up to 4 hertz in field stabilization, and then nodding with the full telescope to get rid of any residual background effects. This is all quite standard. There were some nice explanations this week on the residual that remains after the chopping, and that if you do pupil tracking, which you can do in VISIR, obviously, if you do pupil tracking, that these particular residuals are related to this, to basically that the field rotates, basically because the field rotates, the image is of course reflected by a different part of the mirrors, and so these residuals can be mitigated by pupil tracking in essence. Right, so this is the telescope, this is all standard. Let's switch to the modes that we can do. So I made movies, I uploaded them to YouTube, they should work. So the modes, basically 3 imaging modes, 1 spectroscopy mode. Imaging is standard. Spectroscopy, here the neon 2 lines, the forbidden neon 2 lines of protoplanetary disk and UV evaporation of the disk. And then on the left bottom side, we have sparse aperture masking in real time and chronography in real time on UT3. So this is not near, but standard chronography without a deformable secondary and an AO system. So in the SAM, you can see the piston changes in the snowflake during these observations of a massive ISO. So I will go through each of the modes in a bit more detail. Now you see what kind of things I see on YouTube as delivered by the YouTube AI. Next, why don't you go to the next one? Next. So, modes. This is the sensitivity, median sensitivity for various weather conditions of the 22 or 25 filters that we have, broadband and narrowband filters, stretching the 3 atmospheric windows with the transparency given for 1 millimeter PWV in this particular plot. So the sensitivity is for a point source. It's not the peak flux, but it's for the point source. Peak flux, of course, involve the image quality if you want to have sensitivity there. Note the M bands, which has been offered since 2015 or 2016, and it was discovered late 2018 that there's a leak there. If you want to know more, if you're not aware of this, please see the web pages of VISIR on this particular leak, which was a long wavelength leak. So the M band leaks light from 11 micron or so. So people should be aware of this. So these filters can be found in the user manual, obviously. So the filter profiles can be found in the user manual, and the curves can be downloaded from the web pages too. So what does this image quality then? What is the image quality that VISIR delivers? Of course, VISIR was made with conceived with the idea of delivering image quality of the highest quality. High performance image quality. Here I show the image quality reached for 3 different seeing bins. This is basically an exercise redoing something that was already done by Mario van den Anker and published in an SPIE paper in 2016, but now with more data. So you can see basically at the long wavelength range in the Q band, that Q band stays diffracted. So the dashed line is the diffraction limit, obviously. The model is basically 3 full width half maxes added in quadrature. One that describes the atmosphere, one is the telescope diffraction, and the other full width half max is the instrument. The transference function. But if we look at the data themselves, the dots, you can see that M band is clearly always distorted or has an influenced by the atmospheric turbulence. You can see that N band remains diffraction limited, maybe up to 0.5 arcsecond seeing, and Q band remains diffraction limited about up to 0.9 seeing, where seeing is the optical seeing at 500 nanometers at zenith. Of course, these things are implemented in ETC. If you use ETC for VISIR, then this is what you get. So this is the image quality that VISIR delivers, and shows that people are aware that N-band is not always diffraction limited, which we are all aware of. Then other mode, spectroscopy. The details are here. So there are 3 slit widths, 0.4, 0.75 and 1 arcsecond. There's a long slit, and there's a short slit for cross dispersed, because otherwise it doesn't fit. The spectroscopy arm delivers or offers you 2 acquisition filters, but the acquisition can also be done in the other arm, so the imaging arm, in case your source is brighter in another filter. And as said, it has the same of course detector as the imaging arm. So how does this look on sky for the low resolution prism? Just to give you a feel of how this, what you're looking at if you're at the telescope. Here you see the 1 arcsecond slits. You see the chop nodding in parallel. You can do chop nodding perpendicular. So the chop and the nod, so the M2 and the telescope are moving perpendicular, or you can do it parallel such that the star remains in the slit. And it's 1 arcsecond, so actually the spectrum that you receive, given that the diffraction limit is less than 1 arcsecond, the image, the spectrum that you receive, the sky spectrum, actually has a lower resolution than the actual source spectrum here, with the sensitivities as given on the right hand side. Then in high resolution, VISIR offers then cross dispersed or long slit. The long slit has only a limited 3 settings, 3 order shortening filters that give these 3 settings around molecular hydrogen and neon 2 lines. And the high resolution cross dispersed at 4 arcsecond slit with all slit widths, the 3 slit widths, can basically freely select any part in the N module. So sensitivities for now are about 3 Janskys, but there was a large program, a high resolution program, searching for water in protoplanetary disks, and this analysis seems to suggest that the sensitivity is way better than this, at least 75%. Then SAM mode was explained, and results were delivered in a very nice way by Steph. Got your last name. Just quickly here, the SAM mode has 7 apertures, 21 baselines, and what was shown in the science presentation on MWC297 is clearly the information that you get from the closure phase. And that's why you do SAM, because you want to get the closure phase, so you do not, so you're not no longer dependent on any atmospheric turbulence. So the closure phases that were shown on MWC297, you can see that there was a large spread. There was a lot of information in there, present just in the visibility amplitudes. You could fit it with any Gaussian or uniform disk or whatever. So closure phase is key. SAM delivers you this and provides you with diffraction-limited, sub-diffraction-limited information. And chronography, I'm going to skip this. There's been a lot of chronography, except for the part that with NEAR, there are still elements, or there are elements, NEAR elements in VISIR. And so in the recommissioning of UT2, without an AO system, we need to see what chronography will deliver for VISIR. Calibrations. This slide is just a complicated way to show you what kind of calibrations we take at night. Calibrations are, first of all, we need to see what the mid-infrared transparency is, which is time loss, and efforts are going on to see whether this particular say measurement of the atmosphere to probe the mid-infrared sensitivity can be predicted using the meteorological information, conditions of the sky actually. And there's a talk later on this. So calibrations, we deliver calibrations for imaging and for low resolution, but not for high resolution. That has to be delivered by the PI themselves. I have to go a bit faster. I can skip this. I can talk a bit about this. So any instrument by ESO, there's a bit of a view of how ESO manages an instrument. Any instrument in ESO has an instrument operations team around it. And the instrument operations team basically guides the instrument through its lifetime. The team consists of experts in various fields, so operations, instrumentations, software, and for the people in Garching, the members are from USD, QC, and the pipeline. Okay, and it's the instrument operations team, the IoT, that determines which instrument, or discusses and proposes which direction the instrument evolution should go, which mode should be kept, which modes should be evolved or developed. So for an upgrade, for example, there are some things that are required to have a successful upgrade. So of course, an upgrade can only be motivated and justified if the scientific impact is warranted for this particular upgrade. And then we need to have a data that is delivered. It needs to be calibratable in order to have proper science coming out. If such an upgrade is then deemed to be scientifically justified, we make an inventory of the software, hardware changes, and operational changes, pipeline changes, or archive changes, and then resource requests and approval internally to ESO needs to be done, because there are many things going on with the ESO and we don't have unlimited resources. Then the implementation follows commissioning, and then the call for proposal and integration into operations for the user to use this particular new feature. So the upgrade was done in 2012, where the new Aquarius detector was installed. Water vapor monitor was also installed in Paranal. That is being used on a nightly basis if we're in operations. Low resolution prism was introduced, and Samoa chronography was made possible, and the M-band was put in. I discussed this. You can 1 minute. I see. I just want to highlight that any PWV and predictions of atmosphere and the influence of the atmosphere on the sensitivity can be found in the talk by Alexandra Solars on Friday, and in this paper using near data by Turki et al. So for the near legacy, I mentioned this, the near optical elements are still in there. And so there are 3 things that we are curious about how this will behave in UT2. One of the things is, of course, the chronography, and then the Dickey switch that has been mentioned a couple of times, which provides some interesting opportunities for larger fields or fields with extended mid-infrared emission. And I said we need to recharacterize this on UT2. The L-band, I should note, is approved for operations, and we are busy with putting this in operations as soon as possible. The motivation is that L-band has always been offered in Paranal. With the demise of NACO and with Isaac, there's no L-band opportunities currently. This is the info if you want to know more. Public pages, ESO-wide documents, proceedings, and various tools for VISIR to help you in preparing your observations and to help you in reducing the data and analyzing the data. And then there's a lot of science going on. And I would like to emphasize that keep writing those proposals and keeping doing this science, as without the proposals, without the science, people may think that VISIR is underrated and mid-infrared is underrated, and this should not happen. So this is the summary, VISIR instrument description. I've done this. I thank you for your attention.
Willem-Jan, thank you. We have time for a few different questions. Sorry if you're muted, but we appreciate the applause. If you have a question to ask, I believe our method for doing that is we have the clapping emoji on the participants. Leo, is that the correct way to do this?
Yeah.
And, sure. Okay. Go ahead and check that, and I will look up and down the list here, and we can unmute whoever puts up the emoji.
Sorry, Danny, you can just read the questions that you want to read. For example, Warren had one from the Slack channel.
From where?
From the Slack channel instrumentation.
From the Slack channel.
Should I read the question? Or,
I go ahead, yes.
or Warren, why don't you ask your question yourself? You're online anyway.
There might be problems with the sound. Does that work okay?
I can hear it.
Yeah, we are hearing you.
My question to Willem-Jan then was, what's the most common problems? What are the most common inquiries that users have when they're looking at the data? You know, systematic signatures and any other issues that they find in their reduced data when they're trying to interpret it. What are the most common inquiries that you get?
To be honest, I don't get that many inquiries on the data, the quality that people find spurious, signals that they do not know how to interpret. What I do find is that there's a lot of things going on in the mid-infrared that allows experimenting. I mean, we have a certain model of operating the instrument in the mid-infrared, but it's by far not, I mean, it's not the only way of doing things. And there may be, for certain science cases, there may be alternative ways of observing, of acquiring the data that allow you to suppress certain signals in a better way at different wavelengths. And so what we often get communicated to Paranal is people who would like to experiment. I mean, in the context of the mid-infrared instrument on the ELT, for example, that we would like to, that VISIR can be something like a pathfinder. And we do experiments to see how we could improve the data acquisition, how we could improve the operations, and how we could improve the data quality by doing things a bit different. Job nonning is a way of doing this, but it's not obviously not the only way of doing things. But what people find in their data, I wish if anybody has spurious signals in their data and they would like to interpret this and they have no clue how, please contact us.
Thanks very much.
Okay, let's do one more question, I think. Looks like Claudia Agliozzo. I am going to ask you to unmute. A prompt should come up.
Could you repeat it?
Hello, actually, I just clapped because I enjoyed it.
Oh, okay, sorry. We appreciate your clap.
Question.
Was there a question or was there no question?
I'm not seeing any other hands raised.
There was another question on Slack. Perhaps James de VISIR, perhaps do you want to ask another question? Or I'll just read it. If you can.
Go ahead.
So James asks about how many days a year is VISIR available and what is the present demand?
VISIR is available 365 nights in principle. If VISIR is back on UT2, on the Casablanca UT2, it is offered and available. It's not taken off, it's always there. It can always be used. Throughout the night, we switch from one instrument to the other, depending on the conditions. And so VISIR can be used every single night. You can put in your proposal or every time throughout the year.
And what is the demand?
The demand has, okay, the historical demand was, for the old VISIR, was about 40 proposals or so per 6 months. That went up significantly after the upgrade. But as you can see in the, what is this timeline that I had put somewhere here, VISIR has been busy with all kinds of different experiments. And so stable operations has only been 2 or 3 semesters. So I'm very curious. Mario has better information or more information than me if he wants to jump in, Mario at USD.
I think James is asking for the demand in nights, and I'll answer on Slack because I don't have the number on top of my head, but it must be, yeah. I mean, a typical request would be, the average request would be something like 8 hours, so the demand would probably per period something like that. But I'll get back to you on Slack.